Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. Till now, we have discussed the cases wherein a categorical variable was present as such as an independent variable. Therein, like in the case of dummy variables, we have discussed these things. Like we had a categorical, yes, no type of things, good, bad, or these things like what is your gender, male, female. These things were having something yes or no. These things were incorporated over to the right hand side, means to the independent variable side. They were along with the other variables which were of say ratio scale. They were over there, and we have seen how to deal with them, how to deal with these categorical variables, particularly in our discussion on dummy variables. Today's lecture is on the case wherein these categorical variables, or you can say yes or no type of variables, are the dependent variable. Means now we have them as the dependent variable, and there are other independent variables as such. So in terms of categorical dependent variable, wherein say maybe we are having the probability of having a life insurance of a person. If yes, 1, no, 0. Probability of having a house, yes, 1, no, 0. So now these type of things, when they are, now we are deciding upon what are the say correlates or what are the determinants of having a life insurance. Now we take maybe his income level, maybe even his gender, or maybe other things, his socioeconomic characteristics. Many of those can be incorporated, but we are not concerned with what is the independent variables or what are the explanatory variables, but rather the dependent variable itself is in this format of yes or no. So if that is the case, then we come to the discussion on the how to estimate these models, and the basic theory of it will be covered under linear probability models. Now again, understand this linear probability model. As such, as we will proceed further, we will see that they are not used. The interesting thing is, these linear probability models are practically not used, but they will serve as the basic foundation of what constitutes of the scheme of things wherein the dependent variable is of this nature, where the probability of having is 1 and probability of not having is 0, and likewise. We introduced this linear probability model by considering an incidence of say owning a car. We want to check what is the probability that a person will be having a car or not. So we take a model yi is equal to beta 1 plus beta 2 xi plus ui, where x is your income. Now what is y? Y is the individual status, whether he is having a car or not, and there is a binary response. Yes, if y is equal to 1, that the individual has a car. If y is equal to 0, the individual doesn't have a car. So here your dependent variable is of binary nature, 1 0 1 0. We write this as expected value of y given x is equal to probability of y is equal to 1 upon x. If your x is equal to 1, then the probability y is equal to 1. Means that is the person is having a car. And again, the expectation of your error term u, obviously as generally we had taking it, we will be taking it as 0. and expected value of y by x is equal to beta 1 plus beta 2 xi, where pi is the probability that y is equal to 1 and uh, the probability of not having. So see, probability is p plus q is equal to 1. P is the probability of success, q may be the probability of failure. The probability is equal to 1. So we are not defining here in terms of q, rather we are saying that p is the probability that y is equal to 1 and 1 minus p is the probability that y is equal to 0, meaning thereby y is equal to 0 means that that individual is not having a car. So when we are having only two options, having a car and not having a car, such is this comes under the domain of Bernoulli's probability distribution. It is basically, this Bernoulli distribution is an special case of binomial distribution where there is only one trial, that is n is all equal to 1. Each observation of a linear probability model represents a single trial with a binary outcome, maybe success or failure. Hence, that is why we call it Bernoulli's distribution. So here, expected value of y is equal to 1 multiplied the probability of success p plus 0 into 1 minus p, that is 1 minus p is the probability of failure, which is equal to p. Expected value of y given x is equal to beta 1 plus beta 2 xi, which is equal to pi, the probability of having a car, or probability of success. Now, as p should lie between probability, it lies between 0 and 1. So, as probability lies between 0, 1 and the dependent variable is binary, so expected value of y given x, the probability is equal to y is equal to 1. So, we can say that expected value of y given x, it is more than 0, less than 1, or we can also say that the probability of having probability of success here is the probability of having a car is more than or equal to 0 and less than or equal to 1. So let us define this linear probability model as a model where a dichotomous dependent variable is explained as a linear function of one or a number of regressors. This is because the expected value of y is conditional that the individual has his car, a private car. Y is equal to 1 given that the individual income group is x. So pi is equal to the probability that y is equal to 1, that is the response is positive. 1 minus pi is the probability that y is equal to 0, that the response is negative. Now, in this linear probability model, a key objective is to estimate the conditional probability of a positive response of an event occurring, given whatever certain characteristics as such. And the slope parameter here, that is the B2, it shows the impact of unit change in the individual's income on the probability of the individual having a car. Means you have this yi is equal to beta 1 plus beta 2 xi. Now the slope parameter beta 2, it shows the impact of a unit change in the individual's income on the probability of the individual having a car. So this has an impact on the probability that he will have a car. That is why we are discussing a linear probability model. So this when there is an increase or decrease in the income, what is it impact on the probability that he will have a car or not have a car is what we will determine over here in our discussions. Now, We can do the estimation, fine, but we come to the issues, we come to the problems. So, the very first problem is you are estimating the probability, the result may be more than 1. So, when say Pi is equal to 1, beta 1 plus beta 2x, where Pi, it must fall, it must be equal or less or more than 0 and less than and equal to 1. So, however, there is no mechanism in the model to ensure that the estimated probabilities obtained from the estimates of beta 1 and beta 2 are within this permissible range 0 to 1. Means we are saying probability of having a car, it will not be 1.5. The reason probability can take a value of 1. 1 means yes, it's done. He is having a car. Or probability is 0. 0 means fine, he doesn't have a car. There will nothing a term like -5 or -2 or minus or +1, +2, +4, +5. These terms cannot be there. But when you estimate such a model, your Pi can get such a values. There is nothing in this model which will stop or restrict that. No, this value of Pi, it will not go beyond 1 or not go less than 0. There is nothing in this model. So this is the most basic criticism. But we are learning this because based on this criticism, we will try to avoid the criticism and come up with the alternate models which can handle these type of situations very well. So maybe you can say we estimate the model, and if we check that y hat lies between 0 and 1, fine. There is no problem. We will take, there are other issues of heteroscedasticity and normality, but we will say that fine, we can estimate this model. But the chances are that we cannot restrict it. It may come between 0 and merely by chance. But there is a full-fledged probability that the values may go beyond 0 and 1. So, if not, then we need to use alternate methods like logit, a very popular method like logistic regression, where this y hat will fall, whatever you do, between 0 and 1. So, this is the major criticism of this model. Then linearity. That is, this change in probability at all levels is assumed to be constant. We have a slope coefficient beta 2 is equal to 0.6. Then we can say that when there is a linear relationship in crude terms, we say that if x, the unit of independent variable, increases, the probability of this will increase by a certain amount. But that certain amount is constant for the entire relationship. Now assume a case like having a car. A person is having, say, income of 50,000, 60,000. Okay. Then maybe there is a probability, is a very few, although means theoretically the chance is very poor that this person will have any car or such. Okay. But you are saying that, and when that person, his income, or there is a person whose income is say 2 lakh rupees or 3 lakh rupees, we again say that when his income increased to 2 lakh, 3 lakh rupees, then also there will be a certain probability of him having that car. Now, can you imagine that the probability when his income is 2 lakh rupees of having a car and the probability when his income is 50,000 rupees, in both the case the probability will be same? No. But that is what is being assumed when you are assuming that it is a case of linear, there is a linear relationship. So this Pi upon xi, that is the value of beta 2, measures the change in probability due to the change in income. Since B2 is constant, the change in probability at all the level of income is assumed to be constant. And this is not realistic. So this is again an limitation of the linear probability model. Then a major issue again is of heteroscedasticity. Now here we say that the linear probability model is associated with the problem of heteroscedasticity, which means in the disturbance term, which means that as time passes, the amount of error or the error varies, and our OLS estimator, it becomes inefficient. It is no longer blue. We can do that. We can also prove that y is equal to, say, b1 plus b2 xi, and see, we are not saying that the expected value of ui is not equal to 0. So even if the expected value of ui is equal to 0 and covariance ui uj is equal to 0, means there is no relationship between the previous and this, we cannot assume that the variance of ui is a constant sigma square. Because again we refer back to the discussion on Bernoulli's distribution. In Bernoulli's distribution, the expected mean Ex is E, the mean is equal to the P, and the variance of X is equal to P1 minus P. And that we will prove that P1 minus P means it is changing with time. So in the first case, when y is equal to 1, if you take y is equal to 1, then we can write this equation in terms of ui. So ui you can write as 1 minus beta 1 minus beta 2 xi with probability pi. And in this case, if you take y is equal to 0, if it is 0, then we can write ui is equal to beta 1 minus beta 2 xi, and here the probability is 1 minus p. And the variance is, we can write variance as, since there is a probability of p and probability of 1 minus p, so we write it as 1 minus beta 1 minus beta 2 xi whole square multiplied by pi plus minus beta 1 minus beta 2 xi square multiplied by 1 minus p1. So this is how we are defining the variance of this Bernoulli's distribution as applicable in this case. So once we have derived this, now pi is equal to expected value of y given xi is equal to beta 1 plus beta 2 xi, and 1 minus pi is equal to minus beta 1 minus beta 2 xi. So we write variance ui in the format that 1 minus, it is there is a 1, it is 1 minus beta 1 minus beta 2 xi multiplied by beta 1 plus beta 2 xi plus minus beta 1 minus beta 2 xi square bracket close 1 minus beta 1 beta 2 xi. This we can also write it in this format, that is 1 minus beta 1 minus beta 2 xi multiplied by beta 1 plus beta 2 xi multiplied by 1 minus beta 1 minus beta 2 xi plus beta 1 plus beta 2 xi, and this we can say is nothing but this term, that is 1 minus pi multiplied by pi. So the variance is not constant and it changes with the probability of success, meaning thereby even if the expected value of ui is equal to 0, variance is equal to say you can take sigma square, and covariance, variance is not equal to sigma square, and even the covariance ui uj cannot be 0. It cannot be assumed that the variance ui is equal to sigma square. This is we ignore this term over here. So even if ui is expected value of ui is equal to 0 and covariance of ui uj is equal to 0, we cannot say that the variance of ui is equal to sigma square. So expected value of x is equal to p and the variance of x is equal to p, 1 bracket open, 1 minus p bracket closed. The next issue over here is that of a normality. So this Bernoulli's probability distribution, ui follows a Bernoulli's probability distribution and not a normal distribution. Normality assumption, so we can say when ui is equal to 1 is 1 minus beta 1 minus beta 2 xi and p is equal to pi, and y is equal to 0, u is equal to minus beta 1 minus beta 2 xi and p is equal to 1 minus pi. See, normality assumption is not required for estimation. Rather, estimators need to be only blue, best linear unbiased estimator. But in small samples, significance testing becomes doubtful if your data is not having a normal distribution. So, statistical test based on normal distribution cannot be applied unless the sample size is very large. So, again, this is another issue related with it. So, the problem pi is linearly related to x. This means the major issues. And second thing, we need a mechanism wherein y hat may lie beyond 0 and 1. So, we need to as such restrict it. Again, you understand that case, this linear relationship. So, the probability of an individual having a car increases by 20% when his income increases, say, from 5,000 to 10,000. And when the income increases from, say, 80,000 to 90,000, his probability of having the car is all again 20%. No, this doesn't look logical. Means when the income is less, the probability of having car should increase much, even if there is an increase in income. Even if there is an increase in income, but his income itself is very low, 10,000, 12,000, 20,000, his probability will not increase as such. But only after he has attained a certain particular amount of income, has attained a certain high level of income, the individual is more likely to have a car. So, a linear relationship will not properly represent this situation. Rather, we need a non-linear relationship. So, the solution to these issues is we need a different type of model where the expected value of y given x changes with x, but it remains within the range of 0 and 1. This is the first thing. And second thing, that this relationship, this model should explain or should incorporate the non-linear relationship between pi and xi, so that it approaches both 0 and 1 slowly as x moves. So there should be a non-linear relationship, and the probability should fall between 0 and 1. So this type of model will serve to analyze or estimate the parameters over here. As a solution to this, we can have a cumulative distribution function. Now here it is 0 over here, it is 1 over here, we are having x and we are having y on this axis. We can see that two things are to be seen. Our cumulative distribution function is not going beyond this, is not going beyond 1, and our cumulative distribution function is not going beyond this also. It is not going more than 1, it is not going less than 0. So it falls between 0 and 1. This is the first thing. And second thing, see this, it is not a straight line like this. This cumulative distribution function is not a straight line or an exponentially increasing line like this. It has a definite S structure. Means here it is increasing slowly. Then after a particular point it increases drastically, and then again it has a slow movement. So it is a type of S, you can say. We get an S type of distribution, and this type of distribution we have both, we can have it in a logit or logistic regression or also in probit regression. So if you fit the model of the data with the model of, say, logit, most commonly used as logit, then we can address these issues which we have faced just now.